Hello there, and welcome to the Sleepy Space channel. The most likely way for an interstellar voyage to fail is for absolutely nothing to happen. A generation ship that misses its target does not explode, and it does not stop. It continues at exactly the speed it was given, on exactly the heading it was given, with everybody aboard alive and the lights still on. There are a surprising number of quite distinct ways for that to happen. A break that quietly died 2 centuries early, a destination that turns out to be unusable, a population that reasonably declines to get off, a faster ship launched later that arrives first. Tonight we work through all of them and what becomes of the ship afterward. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. Settle in and let the weight of the day go. Let your shoulders soften. Let your breathing slow and lengthen. There is nowhere you need to be tonight but here. Let's begin. Part 1. The Voyage with no deadline. Every mission humanity has ever flown was declared finished by somebody standing on the ground. There is a room and a console, and a moment when a person with the authority to do so says that the spacecraft has arrived, or that it is lost, and the mission passes into the past tense. That moment is not part of the machine. It is part of the institution that built the machine, and it happens in a building on a planet, among people who are drinking coffee and watching a screen. An interstellar voyage removes that room entirely. The ground is 4 light-years behind and cannot act on anything it sees. Nobody aboard has the standing to declare the mission over, and nothing about the ship's behavior would change if they tried. There is no referee. There is no whistle. There is a vessel moving at a fixed speed through a place with nothing in it, and a date written in an archive, and the two have no connection to one another. This is the first thing to understand about a ship that never arrives, and it is stranger than it first sounds. We are used to failure being an event. A rocket fails on the pad in a matter of seconds. A lander fails in the final minutes of a descent. Even a long mission that ends badly ends at a particular hour with a last signal and a room full of quiet people. Interstellar flight offers none of that structure because the physics that carries the ship forward does not require the mission to still exist. Consider what a generation ship actually does with its time. It accelerates for a while at the beginning, perhaps for a few years, perhaps for a few decades, depending on the drive it carries and how hard it can push without tearing itself apart. Then the engines stop. They stop not because anything is wrong, but because there is no reason for them to continue. In a vacuum, an object that is moving keeps moving. Nothing has to be spent to maintain a speed. Nothing has to be decided. The ship simply continues, and it continues for centuries. That coasting period is not an interlude. It is the voyage. 90% of the journey, and often a good deal more, consists of a vessel traveling in a perfectly straight line, with its propulsion inert and its navigation confirming, year after year, that everything is exactly where it should be. The drive at either end is brief and violent and expensive. The middle is silence. The reason for that arrangement is arithmetic rather than preference. Every additional hour a ship spends under thrust costs propellant, and that propellant must itself be carried, and therefore must itself be accelerated, which costs more propellant still. The relationship compounds viciously. A mission designer facing that arithmetic does the only sensible thing and minimizes the powered portion of the flight to the smallest interval that will do the job, then lets the vacuum carry the vessel for as long as it takes. Coasting is not laziness. Coasting is the only affordable way to cross a distance like this. Our own machines already work this way, on a smaller scale. Probes sent to the outer solar system spend most of their operating lives asleep, powered down to a minimal state, waking on a schedule to check their systems and then returning to hibernation. One recent mission to the far edge of the planetary region spent well over 1,000 days in that condition during its cruise. Nothing was wrong. There was simply nothing to do and a great deal of distance to cover, and the most sensible thing a spacecraft can do with a decade of empty space is very close to nothing at all. We should sit with that arrangement for a moment, because everything else in this episode depends on it. A generation ship is not a vehicle being driven. It is a vehicle that was thrown a very long time ago with enormous care and is now simply traveling. The people aboard are not steering. They are maintaining a world that happens to be in motion, and the motion is the one thing they do not have to work at. The consequence is that failure becomes invisible. If the drive is dead, the ship coasts. If the drive is healthy, the ship coasts. From the outside, and from the inside, and from the instrument readings, these two ships are identical for 200 years. The difference between them is a fact about hardware that nobody will test until the end. The arrival date makes the same problem worse. It is worth being precise here. The arrival date is a prediction, not a deadline. It was calculated at departure from a cruise speed that was itself an estimate, aimed at a star whose position had to be projected forward across centuries because stars move. A ship running a few percent behind that prediction is, in any given year of the crossing, entirely indistinguishable from a ship running exactly to plan. There is no accumulating alarm. There is only a number in a record, drifting slowly out of agreement with reality. And when that date finally passes, nothing happens. This is perhaps the quietest fact in the whole subject. Life support does not change. The reactor does not change. The lights come up at the usual hour, and the crops are watered on the usual schedule, and the air is scrubbed at the same rate it was scrubbed the day before. The date is an entry in an archive that may or may not still be consulted, in a language that has had 400 years to drift, held by an institution that may or may not still consider itself bound by it. There is a hard physical limit underneath all of this, and it is worth naming. Once the mid-course correction budget is spent, the trajectory is fixed. Delta V, the capacity to change velocity, is finite and cannot be replenished. It was loaded at departure as mass, and every gram of it had to be accelerated along with everything else, which is why there is never very much of it. A ship that has used its reserve is not steering badly. It is not steering at all. It is on rails that were laid down before anyone alive was born. There is also no rescue. This deserves to be said plainly, because our instincts on the matter are wrong. A second ship sent after the first would launch decades or centuries later, travel faster, and be entirely unable to match velocity with the vessel it was chasing, without spending its own complete braking budget to do so. Coming alongside a ship at cruise speed is not a maneuver, it is the whole mission. There is no recall, no salvage, no tow, and no version of events in which help arrives. Whatever the ship has aboard on the day of departure is what it will have for the rest of its existence. And the mission itself, it turns out, is not a physical object. Nowhere in the ship's structure is there a component that represents the destination. No sensor detects it. No system depends on it. The mission exists in the minds of the people aboard and in the records they keep, and that is the entire extent of its presence in the universe. A hull does not know where it is going. It only knows how fast it is moving, and it does not really know that either. The ship can, however, know exactly where it is. That much is genuinely solved. Millisecond pulsars are among the most stable clocks in nature, spinning hundreds of times a second with a regularity that rivals atomic standards, and navigation by pulsar timing has already been demonstrated from orbit at accuracies of around 10 kilometers. A ship crossing interstellar space could fix its position with real precision at any moment. This is a good example of a capability that does not help. Knowing where you are and being able to be somewhere else are two entirely different problems, and only the first one has been solved. Communication with the world that launched the ship is similarly precise and similarly useless. At the distance of the nearest star system, a question and its answer are separated by more than 8.5 years. At the midpoint of a longer crossing, a decade or more each way, there is no conversation available at that latency, only a very slow exchange of statements between parties who will each have changed considerably by the time the other one hears them. So the ship travels, and the date passes, and nothing announces itself. The question of whether the mission has failed or has merely not yet succeeded cannot be answered from inside at any point before the arrival would have occurred. For several of the states we will look at tonight, it cannot be answered afterward either. That is the shape of the problem. What follows is an attempt to sort it, to take the phrase "never arrives," which sounds like one thing, and separate it into the several quite different situations it actually contains. Some of them are violent and almost impossible. Some of them are gentle and nearly certain. Every one of them leaves the ship moving. We begin with the ending that everyone imagines first, and that turns out to be the least likely of them all. Part 2. The fast ending that almost never happens. When people imagine an interstellar voyage going wrong, they almost always imagine a collision. Something in the dark, moving fast, in the wrong place at the wrong moment. It is a natural picture, and it comes partly from experience with the space near Earth, which is genuinely cluttered, and partly from a habit of imagining the space between stars as a kind of ocean with debris floating in it. The measured version is different, and we should give it a fair and unhurried hearing, because the rest of tonight depends on accepting the conclusion. The interstellar medium does damage a ship. It does not destroy one. It is a budget item, not a catastrophe, and the distinction matters more than almost anything else in the subject. Begin with the density. The local interstellar medium holds roughly 1/3 of a particle in every cubic centimeter. That is worth restating in comparison, because the number is hard to feel on its own. Air at sea level holds something like 25 billion particles in the same volume. The finest vacuum ever produced in a laboratory holds tens of thousands. The space between the stars is thinner than the best vacuum humanity has ever engineered, by a very large margin, and a generation ship would spend centuries inside it. About 1% of that mass, by weight, is dust rather than gas. These grains run from a few nanometers up to roughly 1/4 of a micron, and they follow a steep size distribution, which is the technical way of saying that small grains vastly outnumber large ones. The distribution matters enormously. It means the ship's experience of the medium is dominated by the smallest particles, encountered constantly, and by the largest ones, encountered almost never. At 1/5 of the speed of light, a single submicron grain carries a few millijoules of energy and deposits it into a spot smaller than a pinhead. That produces a microscopic crater. It vaporizes a little material and it scatters a little more, and then the ship carries on. Multiply that by the number of such encounters across several light years, and the result is an erosion budget, measured in fractions of a millimeter of forward-facing surface. Not a breach. A slow, even, entirely predictable thinning of whatever is at the front. That is why every serious design puts something sacrificial at the front. A forward shield takes the erosion so the pressure hull does not. Ice makes a particularly good one, because it is cheap, abundant in the outer regions where such a ship would likely be assembled, and to some extent self-repairing as vapor redeposits on the damaged face. A shield of that kind is consumed slowly across the crossing, and its consumption is a scheduled cost, planned for at the drawing board, no more alarming than the wear on a brake pad. The standard engineering answer to grain-scale impacts is older than spaceflight's interstellar ambitions and elegantly simple. A thin sheet is held some distance ahead of the real hull, and an incoming particle strikes that sheet rather than the wall. At these speeds, the impactor does not punch through so much as disintegrate, converting itself and a small piece of the sheet into a spreading cloud of vapor. That cloud then arrives at the main wall spread over a wide area and carrying the same energy across a great many square centimeters, which the structure absorbs without difficulty. The trick is not to stop the particle. The trick is to make it stop being a particle. We also have direct evidence about what actually crosses the space between stars, and it is thin evidence, which is itself informative. A small number of objects from outside our system have been observed passing through it, found on their way out rather than on their way in, each one a reminder that material does transfer between stars and that it does so very rarely indeed. Our own neighborhood happens to be unusually clean. The sun sits inside a low-density cavity a few hundred light-years across, carved out long ago by the expanding remnants of ancient exploded stars, and the corridor toward the nearest star systems contains no dense cloud along the way. A route through a region 100 times denser would change all of these numbers considerably, raising both the erosion rate and the drag. That is not the route anyone would take first. The larger grains are where the numbers become interesting. A particle of 10 micrograms, still far too small to see, carries around 1 million joules at 1/5 of light speed. That is a genuine event, comparable in energy to a substantial explosive charge going off against the forward face. It would do real damage. It is also extremely rare along any particular path, because the size distribution falls away so steeply that objects of that mass are separated by enormous distances in a medium already almost empty. Anything larger than that is rarer still, and the rarity increases faster than the size. The interstellar medium is not a debris field. It is a fog, and the fog is almost entirely gas, and the gas is thinner than any vacuum we can make. One component does wear out in a way that matters, and it is not the hull. The braking apparatus a ship carries, a vast loop of superconducting cable, or an enormous sail of thin film, is exposed to that same medium for the entire crossing, and it has far less material to lose. Sputtering by the interstellar plasma removes atoms from a thin film steadily and without interruption for centuries. The erosion that the pressure hull barely notices is a serious matter for the one structure the whole arrival depends on. We will come back to that, because it turns out to be the single most consequential piece of wear on the entire vessel. There is a slow interaction with the gas as well, quite apart from the dust. Neutral hydrogen atoms drifting into the ship's bow region exchange charge with the plasma the vessel generates as it moves, a continuous and undramatic process that contributes to the erosion budget rather than to any risk of collision. It is the difference between weather and an accident. The medium is weather. Then there is the question of hitting something substantial, and here the numbers stop being merely reassuring and become almost absurd. Stars fill something on the order of 1 part in 10 to the 23rd of the galaxy's volume. That is a 1 followed by 23 zeros as a denominator. An object aimed at random and set loose to cross the disk would wait far longer than the present age of the universe, by an enormous factor, before striking one. The galaxy looks crowded in a photograph because the photograph flattens it. In 3 dimensions, it is very close to empty. It is worth pausing on that, because we will need it again later, and it will mean something different when we do. None of this means a generation ship is safe. It means the dangers are internal. The realistic fast endings all originate inside the hull: a reactor lost, a pressure vessel opened, a fire in a closed atmosphere with nowhere for the smoke to go. These are the failures that have actually killed people in spaceflight, and they are the failures most likely to kill people aboard a starship. A fire in a sealed environment is among the most frightening things that can happen in engineering, because the atmosphere that keeps everyone alive is also the thing feeding the flame, and there is no outside to vent to and no fresh air to bring in. There are also slower internal endings that would count as fast in context. A failure in the carbon dioxide scrubbing chain gives a crew hours. A loss of the water loop gives them days. A collapse of the food chain gives them a season. On a voyage measured in centuries, any of these is effectively instantaneous. But here is the point the whole part has been building toward, and it should land quietly rather than sharply. Every one of those failures kills people, and not one of them changes the ship's velocity by an amount anyone could measure. A reactor loss removes power, not momentum. A hull breach vents atmosphere, which produces a tiny thrust for a short time, and then nothing. A fire consumes oxygen and material and leaves the mass almost exactly where it was. The vessel does not slow down. It does not turn. It does not stop. Whatever happens inside, the ship continues at the speed it was given, on the heading it was given, for as long as it would have continued anyway. A catastrophic accident aboard a generation ship produces something that is still traveling, and will still be traveling long after there is anybody aboard to notice. That is the ending everyone imagines, examined honestly. It is real, and it is survivable by the ship if not by the crew, and it does nothing whatsoever to the voyage. Which leaves us with all the other ways of not arriving, and the first of those is the one with the most unforgiving arithmetic behind it. Part 3. The ship that cannot stop. If the ship cannot be destroyed, then the first genuinely likely way of never arriving is the one in which everything goes right and the vessel simply does not stop. It reaches the correct star at the correct moment with the correct people aboard and passes straight through. This failure has the most unforgiving arithmetic behind it of anything in the subject, and the arithmetic is worth laying out slowly because it explains something that surprises almost everyone who meets it for the first time. Stopping is a far harder problem than going. The intuition we bring to this is that braking should be the mirror image of accelerating. You spent a certain amount of effort getting up to speed, so you spend a similar amount getting back down. That would be true if the ship could push against something. It cannot. In empty space, the only way to change your velocity by ordinary means is to throw mass in the opposite direction, and the mass you intend to throw at the far end has to be carried the whole way. That is the trap, and it compounds. Propellant reserved for braking is cargo during the outbound cruise, and cargo has to be accelerated along with everything else, which requires more propellant at the start, which is itself cargo, and so on. The result is that a ship which must stop needs roughly the square of the mass ratio a ship that merely flies past would need. Squaring a number that was already enormous is what pushes self-braking out of the realm of engineering and into the realm of arithmetic that simply does not close. This is why every serious proposal for an interstellar mission that actually stops tries to brake against something external instead. There are two credible ways to do that, and they are complementary in a rather beautiful way. The first is a magnetic sail. A ship deploys a very large loop of superconducting cable and runs a current through it, generating a magnetic field that extends for hundreds or thousands of kilometers around the vessel. That field pushes against the charged particles of the interstellar medium, the same thin plasma we spent the last part dismissing as harmless, and the interaction produces drag. The drag is strongest when the ship is moving fastest, because the particles arrive harder and more frequently, and it fades steadily as the vessel slows. A magnetic sail is therefore superb at the beginning of a braking sequence, and almost useless at the end. The second is an electric sail, which uses charge tethers rather than a current loop, and which behaves in precisely the opposite way. Its drag is weak at high speed and improves as the ship slows. Neither device alone is a satisfactory brake. Handing off from one to the other, magnetic first and electric second, makes the whole sequence work. The numbers are the striking part. Braking from about 5% of the speed of light, using both systems in sequence, takes something on the order of 29 years. Magnetic braking alone runs to roughly 40. Electric alone, roughly 35. These are not typographical curiosities. They are the actual scale of the maneuver, which means the brake is not an event. The brake is an era. Consider what that implies for the people aboard. A child born at the start of the deceleration grows up in a world that is slowing down and will very likely die before it stops. An entire human generation exists inside the braking phase, knowing only a ship that is decelerating, having never experienced the long, steady coast their parents took for granted, and never living to see the stillness their children will inherit. 3 generations touch the arrival: the one that lived in the coast, the one that lived in the brake, and the one that lives in whatever comes after. That generation would also live in a physically different ship. A rotating habitat produces its apparent gravity by spinning, and the direction of that pull points outward from the axis. Thrust from a brake produces its own apparent gravity, pointing along the length of the vessel. The two add together as vectors, which means that for the whole of the deceleration, the floor is not where it used to be. Depending on the design, the interior tilts by some angle and stays tilted for decades, or the whole sense of down rotates through a right angle, so that what was a wall becomes a floor. An earlier video walked through what an arrival would actually involve in some detail, and this is the part of it worth carrying forward tonight. The brake is a change in the shape of the world, sustained for a human lifetime. There is a further consequence that has nothing to do with hardware. A society that has spent 3 centuries with no deadlines at all, no season, no harvest that cannot wait, no external clock of any kind, is suddenly handed a task that must be performed correctly at a specific time, by people none of whom has ever done anything of the sort. The deceleration is the first genuine deadline in the ship's history, and it is imposed from outside by orbital mechanics, which does not negotiate. It is worth noting how weak the thing being pushed against actually is. The interstellar magnetic field runs to about 3 microgauss, roughly 150,000 times feebler than the field at Earth's surface, which is itself weak enough that a small magnet overpowers it. Braking works not because the field is strong, but because the ship is fast and the loop is vast, and the interaction accumulates across decades. It is the gentlest possible way to stop something, applied for long enough to matter. There is a second way to stop, and it comes with a hard ceiling attached. A sail can brake against a star's own light, using the destination's radiation pressure and its gravity together, in a maneuver that threads the vessel through the system on a very particular path. Chaining that maneuver through the stars of the nearest triple system produces a maximum arrival speed of roughly 13,800 kilometers per second. That sounds enormous, and it is, but it amounts to under 5% of the speed of light, which sets a floor of about 95 years on the crossing before anyone has even started. Put those two results together and you arrive at the central inversion of interstellar travel. The faster you go, the less able you are to arrive. There is a cruise speed beyond which no known method can shed the velocity at the far end, and every mission that exceeds it is a flyby whether it intends to be one or not. Speed and arrival are not merely different goals. Past a certain point, they are opposed. So what happens if the brake fails, or was never adequate, or eroded to uselessness across 4 centuries of exposure? The destination arrives, and then it departs. At 5% of the speed of light, a ship covers 15,000 kilometers every second. The whole width of a planetary system, the span from the innermost world to the outer reaches where the comets live, goes by in something close to a day. 400 years of travel, and the place they were going for is present for an afternoon. It would be, in one narrow and rather cruel sense, a magnificent day. The instruments would return the finest observations ever made of another star system, resolved planetary surfaces, atmospheres measured directly rather than inferred, moons and rings and weather systems seen properly for the first time in human history. Every question the mission was launched to answer would be answered in a matter of hours. And the people recording all of it would understand, while recording it, that they were watching it recede, and that their children would grow up somewhere else entirely, and that the somewhere else has no name because nobody has ever been there. Retargeting afterward is essentially impossible, and it is worth being clear about why. The braking system was the Delta V. There is no separate reserve sitting in a tank waiting to be used for a course change, because carrying such a reserve would have required the same compounding arithmetic that made self-braking impossible in the first place. The next candidate star is decades to centuries further along a path nobody surveyed, and reaching it would require exactly the capability the ship has just demonstrated it does not have. A ship that has passed its destination is, from that moment onward, a ship with no destination at all. Fully functional. Fully crewed. Lights on, crops growing, air clean, everyone healthy. Permanently in transit. And the strangest part is that from the inside, the day after is indistinguishable from the day before. The coast resumes, because the coast never really stopped, and the ship continues doing the thing it has been doing since before anybody aboard was born. Part 4. The world that was never there. The third way of never arriving is the one that involves no failure at all. The ship works. The brake works. The navigation is flawless. The crew is healthy. The deceleration completes on schedule, and the vessel comes to rest exactly where it was aimed 400 years earlier. And there is nowhere to go. This state is uncomfortable in a way the others are not, because there is nobody to blame and nothing to fix. Every system performed to specification. The problem was in the decision that was made before departure, using the only information that could possibly have been available, and that information was always going to be wrong in ways nobody could have predicted. The root of it is simple and unavoidable. Every fact used to justify the voyage was carried to Earth by light that left the destination before the ship did. A target 4 light-years away is being described by a photograph taken 4 years ago at the very best, and in practice by observations assembled over decades and extrapolated forward across centuries. By the time anybody can check, the information is older than the mission. Start with what we can actually measure about a distant world, because the gap between detection and understanding is much wider than it appears from a headline. When a planet passes in front of its star, the amount of light it blocks tells us its radius. When it tugs its star gently back and forth, the wobble tells us its minimum mass. Neither number alone tells us what the planet is. The same measurement is consistent with a dense ball of rock and iron, or with a much lighter world puffed out by an enormous atmosphere, and distinguishing between them requires both measurements together plus a known orbital geometry. For the great majority of catalogued planets, we do not have that. Even when we do, the atmosphere often refuses to cooperate. Starlight filtering through the edge of a planet's air should carry the fingerprints of whatever molecules it passed through. In practice, high-altitude haze frequently flattens that signal into a featureless line. Some of the most intensively studied small worlds in the catalogue have returned exactly this result: hundreds of hours of observation and a spectrum with nothing in it. The atmosphere is there. It simply will not say what it is made of. Then there is oxygen, which is the most celebrated biosignature we have, and also the most treacherous. The reasoning behind its reputation is sound. Oxygen is chemically aggressive and disappears quickly unless something keeps replenishing it, and on Earth, that something is life. But there is a second route. Ultraviolet light striking the upper atmosphere of a planet can split water vapor into hydrogen and oxygen, and if the hydrogen is light enough and the planet's gravity weak enough, the hydrogen escapes to space and the oxygen stays behind. Run that process for a few 100 million years, and you have a world with a thick oxygen atmosphere and nothing alive on it anywhere. That is the trap worth dwelling on for a moment. A ship could cross 4 light years on the strength of an oxygen detection, decelerate for 30 years, arrive at the world it was promised, and find a sterile rock wearing the chemistry of a living planet like a mask. Nothing was mismeasured. The signal was real. It simply meant something else. The star itself introduces further complications. Most of the stars near enough to consider are small and cool and red, because such stars are overwhelmingly the most common kind in the galaxy. A planet in the habitable zone of a small red star must orbit very close in, and at that distance, tidal forces lock its rotation to its orbit. One face holds a permanent day, the other a permanent night, and between them runs a narrow ring of endless twilight. That is not necessarily fatal to habitability, and it is a long way from what anybody planning the voyage would have pictured. There is also genuine disagreement about where the habitable zone even is. The conservative definition draws a narrow band where liquid water could persist on a rocky surface under an atmosphere much like Earth's. The optimistic definition widens it considerably by allowing for thicker atmospheres and different greenhouse chemistry. A third definition extends it much further still, to worlds wrapped in deep hydrogen-rich envelopes where an ocean might sit beneath enormous pressure. The same planet can be comfortably inside one definition and clearly outside another, and which definition a mission was planned around is a choice somebody made centuries before anyone could check it. Those same stars flare. Relative to their modest output, small red stars produce outbursts far larger than anything the Sun manages, and a world orbiting close enough to be warm receives them at close range. A planet can be in the habitable zone by every definition and still be scoured on a schedule. Even the air is a trap. Carbon dioxide becomes dangerous to human beings at concentrations far below anything that would look significant on a planetary survey. A few percent impairs judgment and breathing. Around 10% is rapidly lethal. An atmosphere could be listed as broadly Earth-like, with a comfortable pressure and a reasonable temperature, and remain something no person can breathe for more than a few minutes. The system as a whole is the last surprise. Approach is the moment its real architecture is measured properly for the first time. Orbits, resonances, unseen bodies, and the stability zones that govern where anything can persist around multiple stars. Dust matters here too. Astronomers measure the dust in other systems against the level in our own, and some nearby systems carry 100 times as much. Such a system is harder to observe from a distance and considerably more hostile to approach. Navigation inside the destination is its own problem, and a surprisingly large one. Nothing measured from 4 light-years away is remotely precise enough to fly by. The positions of the planets, their exact orbital periods, the locations of moons and debris, and the gravitational field of the whole assembly would all have to be measured from scratch during the approach, by a crew whose entire experience of astronomy consists of looking at one set of unchanging stars through a hull. The map has to be drawn while arriving on it. It would be reasonable to ask how confident we could ever be, and the honest answer is discouraging. The first planet ever confirmed in the habitable zone of a sun-like star was announced more than a decade ago and celebrated accordingly, and it remains poorly characterized to this day. We do not know its mass with confidence. We do not know its composition. We do not know whether it has an atmosphere. That is the state of our knowledge about one of the best-studied candidates in the entire catalogue, observed continuously by our finest instruments, and it is roughly the quality of information any mission would be departing on. Some things, at least, would not be surprises. In a system with more than one star, only certain orbital distances are stable over long periods, and those zones can be calculated in advance from the masses and the geometry without needing to see anything. A planet inside a stable zone will still be there. A planet outside one was never there to begin with. It is a small piece of certainty in a subject with very little of it. And a tidally locked world would have weather of a kind nobody has seen. Air heated permanently on one face and frozen permanently on the other drives a constant wind across the twilight ring between them, blowing in the same direction, without pause, forever. It is a hazard and a resource at the same time, and it is the sort of detail that no measurement from 4 light-years away could possibly have anticipated. So there is a version of this voyage in which the ship stops, surveys, and finds a world that is entirely real, physically present, precisely where it was expected, and unusable. Perhaps it is an ocean with no land anywhere on it. Perhaps its soil is laced with reactive salts. Perhaps its air would kill in 10 minutes, and its star burns everything on the surface every few decades. Perhaps it is merely, disappointingly, not what the measurement said. The mission has arrived. Nobody has arrived anywhere, and the options at that point are narrow. The braking budget is spent, because braking was the budget. The ship is now at rest relative to a star system it cannot use, which is a very different situation from being in transit toward one. It has become a settlement in orbit around a disappointment, or it must find some way to accelerate again toward a target chosen from the same catalogue of unreliable information that brought it here, using capabilities it no longer has. There is an odd mercy buried in that. A ship which fails to stop at least keeps its speed. A ship which stops successfully at the wrong place has given away the only thing it had. Part 5. The Silent Coast. The fourth way of never arriving is the one that hides. It is not dramatic, and it does not announce itself, and that is precisely what makes it the most quietly troubling state on the list. The ship's brake dies somewhere in the middle of the crossing, and nothing changes, because nothing was using the brake. We established earlier that coasting is the ship's normal condition. That fact, which made the voyage affordable, now works against it. A drive that has failed and a drive that is merely idle produce exactly the same result. a vessel moving in a straight line at constant speed. There is no warning light for a failure that will not matter for 200 years, and there is no test that can be run for free. This is a general property of very long engineering projects, rather than a peculiarity of starships, and it is worth stating plainly rather than dramatically. Systems that are not used are not tested. Systems that are not tested degrade unobserved. The braking apparatus aboard a generation ship is simultaneously the most important component in the vessel and the component that will sit unused for the longest continuous period in the history of machinery. Consider what that apparatus actually is. A magnetic sail depends on loops of superconducting cable held at cryogenic temperature, continuously, for centuries. Superconductivity is a fragile state. A loss of it, engineers call the event a quench, can happen abruptly, and when a large current has nowhere to go, it dumps its energy into the conductor as heat, which can damage the loop badly enough that it will never carry a current again. That is not a slow degradation. That is a component going from perfect to worthless in a matter of seconds, in a system nobody was watching, 300 years before anyone needed it. A sail is worse in a different way. It is enormous and it is thin, and it hangs in the interstellar medium for the entire crossing being slowly sputtered away, atom by atom, by the same plasma it will eventually be asked to push against. The erosion the pressure hull barely notices is a serious matter for a film measured in fractions of a micron. The brake is thinnest at the exact moment it is finally required. The natural response is to test it, and testing is where the trap closes. Firing a drive to confirm that it works consumes propellant that was budgeted for arrival, and there was never any spare. Deploying a sail to inspect it exposes it to further erosion and risks damaging the deployment mechanism, which is itself a component that has been sitting unused for centuries. Every act of verification costs some of the thing being verified. A crew can look after their brake, or they can know that it works. They cannot do both. Power declines on a schedule that no maintenance can alter. A supply built around a radioisotope with a half-life of about 87 years has lost half its output in a single long human lifetime, and the conversion hardware degrades independently on top of that. This is not a failure that can be repaired, because it is not a failure at all. It is physics running correctly. A century into the voyage, the ship simply has less power than it started with, and the arithmetic was known at departure and accepted because there was no alternative. Spare parts are the deepest of these problems and the least glamorous. There is no supply chain. Everything that will ever be needed was either loaded before departure or must be manufactured aboard, from recycled material by people who have never seen the original being made and who are working from documentation written in an older form of their own language. A ship can carry duplicates of everything, and duplicates are the standard engineering answer, but every duplicate is mass that had to be accelerated, and every duplicate ages through the same centuries as the original. Redundancy buys probability, not certainty. Moving parts are their own category of scheduled failure. Lubrication in vacuum is genuinely difficult. Liquids evaporate away over years, and the dry films used instead simply wear until they are gone. Every hinge, every bearing, every deployment mechanism on a centuries-long mission is a component with a finite number of operations in it, and most of them will be asked to work exactly once, at the end, after having done nothing for the entire voyage. Hydrogen presents a related problem in a different form. It is the most useful propellant there is and the hardest substance in the universe to keep hold of. Even in excellent tanks, boil-off losses accumulate across centuries, and a reserve that looked entirely adequate on departure day can be substantially smaller by the time it matters. Nothing broke. The tank simply did what tanks do, patiently, for 400 years. The control systems age in their own way. The software that will fly the braking sequence was written by people who died 3 centuries before it runs, in a programming language that may no longer be taught, against hardware that has been repaired and substituted so many times that the original design may no longer describe it. Nobody aboard wrote it. Quite possibly nobody aboard fully understands it. It has never been run. Then there is the question of whether anybody aboard could tell. Diagnosing a failure in a superconducting brake requires competence that must survive 10 or more generations of people who have never operated one. That knowledge does not live in files. It lives in bodies, in the hands of somebody who has done the thing and who learned it from somebody else who had done the thing. And bodies are exactly what a long voyage keeps replacing. A manual can describe a procedure. It cannot supply the judgment to know when the procedure is going wrong. All of which produces 2 very different versions of this failure, and they are worth separating carefully because they lead to entirely different centuries. In the first version, the crew finds out early. Some routine inspection 200 years before arrival reveals that the brake is gone, and the finding is confirmed, and there is nothing to be done about it. The ship now knows, with certainty and with a date attached, that it will not stop. Everyone alive will live their whole life inside that knowledge, and so will their children, and their children's children, and the ship must still be maintained the entire time. In the second version, nobody finds out. The centuries pass in ordinary ignorance. Generations are born and die believing the voyage will end as planned, and the discovery lands entirely on the single generation that reaches for the brake and finds nothing there. Everything before them was untroubled. Everything after them is different. It is not obvious which of these is kinder, and the episode should not pretend otherwise. The first spreads the loss thinly across 20 generations and asks all of them to keep working. The second concentrates it entirely into one and gives the previous 19 a piece that was not real. There is something worth noticing in the first version particularly. A population that knows it will never stop is still obliged to maintain a ship whose stated purpose has been formally removed. The air still has to be scrubbed. The crops still have to be tended. The reactor still has to be watched. All of the work remains, and all of the reasons for the work remain, because the work is what keeps everyone alive, but the reason for the ship is gone, and every person aboard knows it, and they get up in the morning and do the work anyway. Some designs try to escape all of this by making the brake passive rather than active, a structure that cannot be switched off instead of a system that must be switched on. A sail that deploys once and simply is, rather than a drive that must fire correctly at a moment 4 centuries after anyone tested it. The trade is a real one, and it goes both ways. Passive systems fail far less often, and they also remove the crew's ability to choose. A ship that cannot help but brake is a ship that cannot decide not to. From the outside, none of this is visible. A coasting ship with a dead brake and a coasting ship on a perfect trajectory look identical from Earth for as long as anyone cares to look. The telescopes see the same thing. The tracking sees the same thing. The distant, faint transmissions say whatever the crew chooses to say, and arrive years late, and by the time they arrive, the people who sent them have moved on to other concerns. The ship travels on, exactly as fast as it ever did, with the quietest possible catastrophe sitting somewhere in its structure, waiting for a century that may never come. Part 6. The empty hull. The fifth way of never arriving removes the people and leaves the machine. This is the version most listeners will have pictured when they heard tonight's title, The Ghost Ship, drifting, lit and empty, and it deserves to be described carefully rather than atmospherically, because the interior of a sealed world without anyone managing it does something specific and measurable rather than something merely eerie. The first thing to correct is the idea that a closed ecosystem runs itself. It does not. A closed ecological system is held inside a narrow band of conditions by continuous intervention, and the moment the intervention stops, it leaves that band. This is not a theoretical claim. It comes from the only serious sealed biosphere experiment ever conducted at scale, and the numbers from it are the most useful thing in this entire subject. In that experiment, a large sealed habitat on Earth was stocked with soil, water, plants, and people, and closed. Oxygen in the atmosphere fell from the normal 20.9% down to around 14% over roughly 15 months. That is a decline of about 140 parts per million every day, sustained for well over a year, in a facility with people inside who were actively trying to prevent exactly that. The cause turned out not to be one thing, which is the part worth remembering. The soil had been made too rich, and the microbial community living in it respired far more vigorously than anticipated, consuming oxygen faster than the plants could replace it. That alone would have been recoverable, because the carbon dioxide produced should have gone back into the plants and closed the loop. Instead, a great deal of it was absorbed into the concrete of the structure itself, which had not been sealed, and the carbon left the cycle permanently. The loop was not a loop. It had a hole in it that nobody had drawn on the diagram, and a slow leak of roughly 1% of the atmosphere per day masked the trend for months. That is the deeper lesson, and it applies to every closed system anybody will ever build. They drift in ways that conceal themselves, and the concealment is not deliberate or exotic. It is simply that several processes are running at once, and the sum of them looks stable for a while. Now set that against the scale of what a generation ship's loop is doing. One person consumes roughly 0.84 kilograms of oxygen a day and produces about a kilogram of carbon dioxide. They need tens of kilograms of water in circulation. They give off around 100 watts of body heat continuously, which sounds small until you multiply it by a population. And they require somewhere between 20 and 40 square meters of growing area to be fed. Every one of those numbers is a flow that must be balanced, and every balance requires somebody to be watching. Take the people away, and the sequence is fairly predictable. The crops go first, because crops in a controlled environment are monocultures, and monocultures fail completely rather than partially. A single pathogen moves through a species in weeks. A nutrient imbalance nobody corrects removes another. A light cycle that drifts because nobody reset it removes a third. Each loss shortens the chain that was keeping the atmosphere in balance, and each shortening accelerates the next. Not all of the loops have the same margin, and it is worth knowing which one runs out first. Carbon dioxide scrubbing is the most critical function aboard any sealed habitat, and the one with the least slack in it. A failure there is measured in hours. Water recovery is more forgiving but never perfect. Real closed systems run at high efficiency and still lose a little to chemistry and to leaks, so a sealed habitat is always very slowly drying out, no matter how carefully it is managed. Food is the most forgiving of the three, and the hardest to restart, because a failed harvest cannot be recovered until the next one. Soil deserves a mention of its own, because it is easy to think of it as a raw material, and it is nothing of the sort. Soil is a biological product. It is a living community of bacteria, fungi, and small organisms that has to be maintained as carefully as any of the crops growing in it, and a ship's growing medium is an engineered artifact with its own health and its own ways of failing. When the people stop tending it, the soil is not simply left alone. It changes into something else. The microbial community simplifies alongside them. Sealed environments consistently lose biological diversity, and what remains is dominated by a small number of organisms that happen to tolerate the specific conditions of the enclosure. Fungi, in particular, are extraordinarily persistent colonizers of sealed human spaces and have caused genuine operational problems aboard real long-duration spacecraft. What survives is not what was planted. It is whatever the enclosure turned out to favor. From there, the outcome forks entirely on one question: does the power hold? If it does, the interior stays warm and lit and humid, and the atmosphere drifts steadily toward whatever the surviving biology and the exposed structural materials drive it to. Oxygen falls. Carbon dioxide climbs or is absorbed and lost. Trace gases accumulate, with nothing to scrub them. The result, after some years, is a place at full pressure and comfortable temperature, brightly illuminated on a schedule nobody set, in which nothing can breathe. No pressure alarm would ever trigger, because the pressure is fine. Only the chemistry is wrong. If the power fails, the outcome is completely different and much simpler. Far from any star, a hull has nothing to warm it. It radiates its heat away into a sky that is a few degrees above absolute zero, and it keeps radiating until it approaches that same temperature. Everything inside freezes solid. Then, slowly, it freeze-dries, as water sublimates directly from ice into vapor and finds its way out through whatever small leaks the structure has. That process preserves biological material remarkably well. A cold derelict would retain recognizable remains and intact, viable-looking seed stalks for an extraordinarily long time. There is one component that keeps working perfectly regardless. Radiation shielding built from water tanks or from stored waste continues to do exactly its job after everyone is gone, because it works by simply being there. That is part of why the interior settles rather than continuing to degrade. The cosmic radiation that would slowly break down organic material is still being stopped by walls that require nothing from anybody. The ship protects its own contents indefinitely, which is either a small mercy or a rather bleak joke, depending on the hour of the night. The timescale of the whole transition is the surprising part. This is not a slow decay across centuries. Within months, the atmosphere is measurably wrong. Within a decade of the last person, the interior is unrecognizable. Within a century, it is chemically stable, and having reached stability, it will then remain that way, essentially forever, because there is nothing left to react and nothing arriving to change it. An earlier video examined at some length what a sealed population does to human biology, and that ground is not worth covering again tonight. What matters here is only the endpoint, however the people go, slowly or all at once, or across generations of dwindling numbers, the ship does not notice. Life support is not a passenger. It is a machine that continues running until it stops, on its own schedule, and the vessel's velocity is not among the things it controls. We are halfway now, and it is worth gathering up what we have before going on. We began with a ship that cannot be destroyed, because the space it travels through has almost nothing in it to strike. We moved to a ship that reaches its destination exactly on schedule and cannot stop, because stopping was always the harder half of the problem. Then to a ship that stops perfectly, at the right star, beside a world that turns out to be unusable, no error anywhere, and nowhere to go. Then to a ship whose brake failed quietly in the middle of the voyage, 2 centuries before anyone would have reached for it, with no way to tell. And now to a ship that outlives everybody inside it and carries on with the lights on. 5 different failures, arising from 5 unrelated causes, at 5 different points in the crossing. And the thread running through all of them is the same, and it is very simple. In every single case, the vessel is still traveling. Not one of these failures slows the ship by an amount that any instrument could measure. Whatever else goes wrong, the motion continues. That observation is what the rest of tonight is built on. If the ship keeps going regardless, then the question stops being how a mission fails and becomes something else entirely. What happens next, and for how long, and where does it end up? Part 7. What a dead ship becomes. Having established that the vessel outlasts its crew, the obvious next question is how long the object itself endures. The answer is longer than almost anything else our species will ever make, and the reasons are the exact reverse of every intuition built on the surface of a planet. Think for a moment about what actually destroys things here. Oxygen destroys things. It is the most chemically aggressive common substance on Earth, and rust, rot, and fire are all versions of the same reaction. Water destroys things by dissolving them, freezing inside them, and carrying them away. Biology destroys things with remarkable efficiency because a great many organisms make their living by taking other structures apart. Gravity destroys things, slowly, by asking every load-bearing element to hold itself up for the whole of its existence. And temperature destroys things through cycling, the endless daily expansion and contraction that opens cracks and works fastenings loose. Interstellar space has none of that. No oxygen. No water. No biology. No gravity load once the ship is coasting. And after an initial period of settling, essentially no temperature change at all. Deep space is the finest preservative in the universe, and a derelict starship is an object placed inside it deliberately. That last point about temperature is worth expanding, because it is genuinely counterintuitive. Metal fatigue on Earth is driven overwhelmingly by repeated cycling. A structure that heats and cools every day accumulates microscopic damage at every cycle, and after enough cycles, a crack begins. A hull that reaches one temperature and simply stays there does not accumulate that damage at all. The cold of deep space is often described as a hazard, and for living systems it certainly is, but for structural steel, it is very close to eternal life. Some things do change. Clean metal surfaces in vacuum, with no oxide layer to separate them, can bond directly to one another where they touch. Engineers call it cold welding, and it has caused real failures on real spacecraft mechanisms, which is why moving parts intended for vacuum are built from deliberately dissimilar materials with treated surfaces. On a derelict, it hardly matters. It seizes the hinges and welds the bearings, and the structure carries on regardless. Sublimation continues too, even for solids, but at temperatures near absolute zero, the rates are so slow as to be meaningless for metals and ceramics across geological time. A steel plate in interstellar space is not losing measurable material. It is simply there. Micrometeoroid pitting has been modeled for the objects we have already sent out, and the results are gentler than most people expect. Beyond the solar system, the density of impactors falls away sharply, and the expected surface damage after millions of years is modest, a fine roughening rather than an excavation. The most exposed spacecraft humanity has ever launched are in a real sense barely being touched. The genuine weak point is polymers. Everything soft in the ship, seals, gaskets, insulation, adhesives, wire coatings, the flexible components that make a complicated machine possible, is built from long molecular chains, and cosmic radiation breaks long chains. Across millions of years, every polymer aboard embrittles, cracks, and eventually crumbles, while the metal structure around it does not change in any way a person could see. The derelict ages from the inside out, losing its soft parts first, becoming steadily more skeletal and steadily more permanent. The radiation dose behind that is around 1.8 millisieverts per day on unshielded material in interstellar space. In biological terms, that is an enormous figure, which is why shielding matters so much for a living crew. In structural terms, it is modest. It discolors glass, producing what physicists call color centers, defects that darken transparent material in proportion to the dose it has received, so that a window becomes, over long enough, a rough record of how long the object has been out there. It displaces atoms in metal lattices without compromising the bulk. It is a slow chemical weathering rather than a destructive force. Power ends on a schedule that can be worked out in advance. A radioisotope source built around a substance with a half-life of about 87 years, combined with steady degradation of the conversion hardware, falls to a small fraction of its original output within a few centuries. Fission reactors need active control and a fuel supply and end sooner. Either way, the ship goes dark on a timetable, and the timetable was known before it left. After that, it is a cold object. It stops transmitting. If the bearings have seized, it stops rotating, though angular momentum being what it is, a ship left spinning may well keep spinning for a very long time. It stops being detectable by anything short of a close inspection, and there is nothing out there to inspect it. Erosion continues on the forward faces, because those still meet the interstellar dust head-on. The trailing surfaces meet nothing at all and remain essentially pristine indefinitely. A derelict starship is therefore an asymmetric object, scoured and pitted on one side, untouched on the other, for as long as it exists. Which brings us to the actual number, and it is a startling one. The realistic verdict is that the hull remains structurally recognizable for hundreds of millions of years, and quite possibly for billions. Not recognizable as a wreck, recognizable as a ship, with its shape intact, its proportions clear, and its engraved markings still readable by anything with eyes and a light. We have direct evidence for this, because we have already launched objects of exactly this kind. The probes sent out of our solar system last century are expected to remain intact, with their engraved plates still legible, on timescales far longer than the surface of the Earth will retain any human structure. Every building, every monument, every carving on this planet will be erased by weather and tectonics and ice long before those small machines show meaningful wear. The most durable things our species has made are not on the ground. They are already gone. The archive inside a generation ship would fare unevenly, and the unevenness is instructive. Magnetic storage fails within decades. Optical discs fail within decades to centuries. Anything relying on a battery, a pressurized gas, or a liquid is finished within a few hundred years at most. But information engraved into metal survives as long as the metal does, and information written into fused quartz glass by laser has been demonstrated to endure extreme heat and radiation, and is plausibly rated for millions of years. That last point about the archive is worth turning over, because the difficulty is not where most people assume. Preserving the medium is very nearly a solved problem. Preserving the reader is not. A perfectly intact disk is a piece of scratched plastic without a machine to spin it, an optical system to read it, a controller to interpret the signal, and a format specification to make sense of the result. Every one of those is a separate thing that has to survive, and formats and readers are lost far faster than the media they were written on. The standard answer is a layered archive, a base level written large enough to be read by eye, with no machine at all, describing how to build the machine that reads the next level up. Whether such a scheme could actually bootstrap itself is untested, and by the nature of the problem will remain untested. So the ship becomes a very particular kind of object. Not a wreck, and not really a vehicle anymore, since there is nobody to be carried and nowhere to be carried to. It becomes an artifact, a sealed, frozen, radiation-hardened container of a civilization's account of itself, moving in a straight line, at a speed nothing can alter, through a place where nothing happens. It is worth asking whether anyone could find such a thing, and the answer is almost certainly not. A working starship is the loudest object imaginable in one particular sense. It must dump enormous quantities of waste heat, and radiators large enough to do that glow in the infrared and cannot be hidden by any means known to physics. A dead ship has no such signature. It is a cold body a few kilometers across, radiating at a handful of degrees above absolute zero, indistinguishable from the background at any meaningful distance, moving through a volume so large that pointing a telescope at the right piece of it would be a matter of pure luck. If the galaxy contains derelict starships, and it may well, the expected number that have ever been observed by anybody is 0. There is one more preservative worth naming, and it is the absence of anything to react with. Chemistry needs partners. A steel plate rusts because oxygen is available. A polymer degrades in sunlight because photons of the right energy keep arriving. Out beyond the last star's meaningful reach, the supply of reaction partners approaches nothing at all. The ship is not merely protected from decay. It is in a place where most kinds of decay have no mechanism available to them. And it will keep doing that for longer than the Earth has left. Part 8. Where it goes. A ship that never arrives still has a trajectory, and a trajectory still leads somewhere, even when the mission does not. This part follows the object outward, and it contains the single most counterintuitive fact in the whole subject. The first thing to establish is that nothing in the galaxy is standing still, including the place the ship left. The Sun carries its entire system around the center of the Milky Way at roughly 230 kilometers per second, completing one circuit in something over 200 million years. Everything we think of as fixed, the constellations, the nearby stars, the whole familiar architecture of the night sky, is a snapshot of a very slow and very large rotation. A probe leaving the solar system does not step outside that motion. It simply becomes one more object in the galactic disk, following its own slightly different orbit around the same center, drifting gradually relative to its neighbors, for as long as the galaxy holds its shape. There is a second layer of motion underneath that one. The Sun is also drifting relative to the stars immediately around it at about 20 kilometers per second toward a point in the constellation Hercules. The stellar neighborhood is not a fixed arrangement that we are moving through. It is a loose crowd of objects all moving somewhat differently, slowly reshuffling itself across hundreds of thousands of years. Any long-term prediction about which star a probe will pass near is therefore an approximation, and the further out the prediction runs, the softer it becomes. Stars pass close to us as well, on timescales that are long by human standards and short by astronomical ones. One small star came within about a light-year of the Sun some 70,000 years ago, brushing through the outer reaches of the comet cloud, and nobody who was alive at the time would have noticed anything at all. The machines we have already sent out are exactly in this category. They are moving at around 17 kilometers per second relative to the Sun, which sounds fast and is nothing at all on this scale. They are far too slow to escape the galaxy. They will orbit the center indefinitely, rising slightly above the disk and settling back into it, wandering slowly with respect to the stars around them, essentially forever. Their predicted approaches to other stars are instructive precisely because of how unimpressive they are. In roughly 40,000 years, one of those probes passes within about 1 7/10 of a light-year of a small nearby star. Another, on a quite different heading, is aimed in the general direction of a bright red giant that it will reach in something like 2 million years. Neither of those is an arrival by any reasonable definition. A separation of 1 7/10 of a light-year is more than a third of the distance to the nearest star from here, which is to say, the probe would pass through a region where that star is merely the brightest thing in the sky, rather than a place with any physical presence. Nothing would happen. Nothing would be seen. If the probe were still transmitting, which it will not be, it would report exactly the same emptiness it had been reporting for 40,000 years. Aiming is complicated by all of this, in a way worth mentioning. A ship is not aimed at where its target star is. It is aimed at where the star will be when the ship gets there, which at these distances and these travel times is a substantial correction. The destination moves measurably across the sky during the voyage. Getting that right requires knowing the star's motion very precisely, and the precision of that knowledge is itself one more thing that was fixed at departure and cannot be improved from aboard. A real generation ship changes this picture completely, and here is the fact worth sitting with. Escape velocity from the galaxy, in the Sun's neighborhood, is somewhere around 550 kilometers per second. That is the speed at which an object stops being bound to the Milky Way at all and begins the long climb out of it. It is a large number by the standards of anything we have built. It is a very small number by the standards of interstellar travel. A ship moving at even 1% of the speed of light is traveling at 3,000 kilometers per second. That is more than 5 times the galaxy's escape velocity. A ship at 5% of light speed is moving at 15,000, nearly 30 times faster than the Milky Way can hold on to anything. So any generation ship fast enough to be worth launching is, by that same speed, fast enough to leave the galaxy entirely. This is not an exotic outcome or an edge case. It follows directly from the arithmetic that makes interstellar travel possible in the first place. A ship that fails to stop where it was aimed does not settle into some quiet orbit among familiar stars. It goes out. It crosses the remainder of the disk in a few 100,000 years, passes through the halo, and then keeps going into a region where there is essentially nothing. Beyond the disk, the medium thins by orders of magnitude. Intergalactic space holds something on the order of 1 particle per cubic meter, against the third of a particle per cubic centimeter we started with, and it contains almost no dust at all. The steady erosion that had been slowly wearing down the ship's forward face effectively stops. The derelict, having survived the crossing, enters somewhere even gentler, and the odds of striking anything remain exactly what they always were. Recall the figure from earlier tonight. Stars fill something on the order of 1 part in 10 to the 23rd of the galaxy's volume, and a randomly aimed object would wait far longer than the present age of the universe before hitting one. The honest estimate for a physical collision runs to something like 10 to the 19th years, roughly 1 billion times the age of everything. That number was reassurance when we first met it. It meant the voyage was survivable. Here it means something considerably heavier, and it is the same number, unchanged. The emptiness that made the crossing possible is the emptiness that makes the derelict permanent. There is nothing out there to stop it. A ship that never arrives cannot crash into anything, cannot fall into anything, cannot be caught by anything, and cannot wear away against anything. It has no mechanism available to it for ending. It can only continue. That is the closing of the last door. Every other object we know about has a way of finishing. Planets are eventually swallowed or scattered. Stars burn out. Even galaxies merge and rearrange. A derelict starship on an escape trajectory has none of those futures available. It is too small to be found, too fast to be held, and traveling through a medium too thin to slow it. The galaxy's escape velocity is not quite a single number, and the uncertainty is honest rather than embarrassing. It depends on how far out from the center you are, and it depends on the total mass of the dark matter halo surrounding the whole system, which is constrained but not precisely known. Different methods give somewhat different answers. What none of them changes is the conclusion: whichever figure turns out to be right, it sits in the hundreds of kilometers per second, and an interstellar cruise speed sits in the thousands or tens of thousands. The margin is not close. It is also worth saying that objects genuinely do leave. There is already a population of stars that have been flung out of the galactic disk by encounters near the center and are now traveling outward on unbound trajectories, and the interstellar visitors that have passed through our own system demonstrate that smaller material transfers between stars routinely. Nothing about a departing derelict would be unprecedented. It would simply be the first one with a name. On the longest timescales, the galaxy itself will change around it. The Milky Way and Andromeda will merge in a few billion years, in a slow rearrangement lasting hundreds of millions of years, during which the two great disks pass through one another and settle into something new. A ship that left early enough would be outside both of them by then, far enough out that the whole event is a change in the geometry of two smudges of light behind it. Further out still, the accelerating expansion of the universe takes over. Gravitationally bound groups of galaxies hold together, everything else recedes and eventually passes beyond reach. A ship traveling outward from a galaxy in a bound group has a genuinely finite set of places it could ever get to, and it will not get to any of them, because it is not aimed at any of them, and there is no one aboard to aim it. The trajectory simply runs on. Straight, steady, unhurried, at a speed set 400 years ago by people whose names are on a plate somewhere inside, through a place that has nothing in it and will keep having nothing in it for as long as there is anything at all. Part 9. The ship that chooses not to arrive. Every state we have looked at so far is something that happens to the ship. This one is something the ship decides. It is the most uncomfortable entry in the whole taxonomy, because nothing has broken, nobody has erred, and the reasons for it are good. The framing to avoid here is judgment, and it is worth being deliberate about that, because the temptation runs the other way. A crew that declines to disembark is not weak, not lost, and not a betrayal of anything. They are the first people in history to be asked to leave a functioning world for a hypothetical one, and the case against doing it is considerably stronger than it looks from 4 light years and 4 centuries away. Start with the simplest fact. By the time the destination is reached, the ship is not a vehicle to anybody alive. It is the world. Every person aboard was born inside it, grew up inside it, learned everything they know inside it, and will very likely die inside it. The planet outside the windows is a place they have only ever encountered as a record, a set of numbers, a rendering, a description written by people who died 3 centuries ago and who had never seen it either. Then there is the physiological argument, which is the hardest of them and the one least often considered. Bone mineral density falls at something like 1 to 1.5% per month in weightlessness, and a rotating habitat is very often designed for less than a full Earth gravity, because a lower spin gravity permits a smaller radius and a slower rotation, and therefore a very much lighter ship. People raised in that environment are not simply out of practice for a full gravity world. They are structurally unsuited to one. And the adaptation runs asymmetrically. Those born to a spinning habitat adapt to it completely and without difficulty, while those arriving from elsewhere never fully do. The ship-born are perfectly at home in the only place they have ever been, and would be permanently uncomfortable anywhere else. There is an epistemic problem underneath that, with no clean answer. Only the ship's interior has ever been tested. Every claim about the destination is inference, from measurements taken by instruments nobody aboard has seen, interpreted by methods nobody aboard has verified, describing a place nobody aboard can check. A population that has spent centuries learning, correctly, to trust only what it can measure directly has a genuinely reasonable basis for treating the destination as theory rather than as fact. That habit of mind is exactly what kept the ship alive, and it is what argues against getting off it. The human evidence we have is thin but pointed. The longest confinement study ever run put 6 people in a sealed facility for 520 days, simulating a mission to Mars. The group averages were good. The individual variation was very large. Some participants sailed through, others struggled considerably, and there was a recognizable slump in the 3rd quarter of the mission, in the stretch furthest from both the departure and the arrival, when neither end of the experience was close enough to hold on to. A generation ship is that 3rd quarter for 200 years. Language drifts as well, and it drifts measurably. 4 centuries is roughly the distance between us and the English of the early 1600s, readable with effort, but not the language anybody speaks. A charter written at departure becomes, by the middle of a long voyage, a text in an older dialect studied by specialists, quoted at ceremonies, and understood mainly through commentary. The instructions are still there. They have stopped being instructions and become literature. There are ways to slow that drift, deliberately, and they are older than any technology aboard. A frozen liturgical dialect, a preserved older form of the language, maintained specifically for ceremonial and legal use, learned formally rather than absorbed, is a real historical mechanism, and it has kept ancient texts readable across far longer spans than a generation ship's voyage. It would work. It would also change what the founding documents are, not a set of instructions being followed, but a sacred text being recited, which is a different relationship to the same words. Some concepts lose their reference entirely. Words like weather, horizon, and sky can survive perfectly well in an archive, while nobody aboard has any experience to attach to them. A child can learn that rain is water falling from the air, and can picture it accurately, and can still have no idea what it means, in the way that a person who has read about grief is not the same as a person who has felt it. The destination is described in a vocabulary that has quietly emptied out. Given all of that, the most likely form of refusal is not a vote and not a mutiny. It is deferral. A decision to continue for now and reassess at the next opportunity, taken once for perfectly sensible reasons, and then taken again and again, until continuing is simply what the ship does and nobody remembers proposing it. Deferral is also the only genuinely reversible non-arrival on this entire list, at least in principle, which is precisely what makes it so easy to keep choosing. Nothing is being given up permanently. The option remains open. It merely remains open for another generation and another, and the breaking window closes quietly somewhere in the middle of all that reasonableness. There is a version where the mission's authority does not collapse so much as evaporate. Nobody abolishes the destination. There is no dramatic session in which the voyage is declared over. It just gradually stops being the reason anyone does anything. The maintenance continues because the maintenance keeps people alive. The schools continue because children need teaching. The institutions continue because institutions are good at continuing. and the destination becomes a piece of history, respected, commemorated, and entirely inert. We should be honest about how ordinary that would be. The only human institutions with a demonstrated record of 2,000 years of continuity are religious ones, and they achieve it by ritualizing practice rather than by preserving instructions. Identity transmits across a millennium. Specific operational tasks do not. And the arrival procedure is an operational task, the most demanding one in the ship's history, to be performed once, correctly, by people whose ancestors last rehearsed it 400 years earlier. Who gets to make the decision is its own question, and the answer is probably not the one the founders imagined. In a small, closed population, occupational roles tend to become hereditary within about 3 generations, simply because children learn what their parents do, and there is nowhere else to learn anything. Whatever structure was written into the charter, the people with the standing to decide about an arrival 4 centuries later will be whichever families have inherited the standing, and that is not something a document can prevent. It is also worth remembering that selection can only ever act on the founding crew. The first generation can be chosen for temperament, for resilience, for enthusiasm about the mission, for whatever qualities the planners think matter. Every generation afterward is simply whoever happens to be born. The population's appetite for risk, its attachment to the destination, its willingness to step outside onto an unknown world, none of these are design parameters after the hatch closes. They are whatever they turn out to be. A large enough ship has one further option, and it is the only architecture that supplies anything resembling an outside. It can split. One population breaks, and one continues, and both are answered. That requires a vessel with enough redundancy to divide, which is a very expensive thing to build for a contingency nobody wants to name at the design stage. A ship without an arrival still has to mark time somehow, and manufactured calendars are a well-documented feature of long isolation. Wintering crews at remote research stations invent festivals. Long-duration spacecraft crews observe anniversaries that mean nothing to anyone outside the vehicle. A generation ship would do the same thing on a much larger scale, and over centuries those invented occasions would become the real calendar, the departure anniversary, the midpoint, the founding of this or that section, the birthdays of people nobody remembers. The scheduled arrival date would sit somewhere in that calendar as one entry among many, and there is no particular reason it would remain the most important one. And so the ship goes on. Not because anything failed, and not because anybody gave up, but because a functioning world full of healthy people declined, reasonably, to leave it, and then went on declining, gently, for as long as anybody was around to decline. Part 10. Arriving last. The 10th state is the strangest of all of them, because in this one the ship arrives. It breaks correctly, at the right star, beside a usable world, with everybody aboard alive and the systems in good order, and the whole 400-year enterprise completed exactly as designed. And it still does not arrive, because somebody else got there first. This follows from an observation about technological progress that is simple, slightly cruel, and difficult to argue with. If the achievable speed of a spacecraft improves over time, then a ship launched later travels faster. And if it travels sufficiently faster, it overtakes the earlier ship in flight and reaches the destination before it. There is therefore an optimal departure date for any given target, and leaving before that date does not get you there sooner. It merely guarantees that you will be passed. The formal version of this idea is sometimes called the incentive trap, and the arithmetic behind it is not exotic. Assume a modest long-run rate of improvement in achievable cruise speed, a small percentage per year, compounding. Then, for a sufficiently distant target, The earliest possible arrival is achieved not by departing immediately, but by waiting several centuries and then departing in something much faster. Every mission launched before the optimal moment arrives after a mission that had not yet been conceived when it left. The trap does have a ceiling, which is worth mentioning because otherwise the argument runs away with itself. Speed does not improve forever. Achievable cruise velocity is bounded by the energy available to accelerate a mass, and that energy is bounded by what a civilization can generate and afford to spend on one project. The improvement curve flattens, so the optimal wait is finite rather than infinite, and there is a real moment at which departing becomes the right decision. The difficulty is that nobody can identify that moment from inside it, and every generation that waits has an excellent argument for waiting a little longer. The crew can run this calculation themselves, which is its own peculiar burden. Everything needed to work out the odds of being overtaken is knowable aboard: the distance remaining, the current speed, and whatever news of propulsion development has reached them from home. A ship's navigators could, at any point in the crossing, compute the probability of their own obsolescence. Whether they would choose to is a different question. The consequence for the first ship is severe and entirely unavoidable. It spends 4 centuries in transit, breaks for 30 years, completes its survey, descends toward its new world, and finds a settlement that has been there for 300 years. With its own history, its own institutions, its own accent, its own holidays, its own version of the events that led to all of this, and no particular need for several thousand new arrivals. The overtaking would not even be a surprise. The later ship's departure would be announced from Earth, and the announcement would travel outward at the speed of light, while the first ship crawled along at a few % of it. The news would arrive decades or centuries before the destination did. There would be nothing to do with it. The ship cannot accelerate. The propellant is gone. It cannot turn back. The propellant is gone. It cannot even shout ahead effectively because the second ship is faster and the message is only marginally faster still. That is a genuinely novel human situation, and it deserves a moment. A population would know, with certainty and with a date attached, that the purpose for which their ancestors were sealed into a metal world had been accomplished by other people, and that they were still obliged to complete the journey anyway, because there is nothing else to do. Their grandparents' great work becomes, in a single transmission, a historical footnote, and they still have 150 years of maintenance ahead of them. The mirror version is equally plausible and considerably lonelier. Nobody follows. Earth stops launching ships because launching them proved impossibly expensive, or because attention moved elsewhere, or because Earth itself stopped. The ship arrives at its target and is the only human thing within 4 light years, with no one to report to, no second wave behind it, and no civilization waiting for the message that the mission succeeded. In both versions, the physical arrival is a complete success, and the meaningful arrival never happens at all. The difference between them is only whether the ship is redundant or alone. If the two populations did meet, the meeting would be strange in ways that have nothing to do with technology. 3 centuries of separate development produce substantial divergence, and the divergence would be cultural and linguistic long before it was anything else. Different vocabulary, different assumptions, different accounts of the same founding history, each side certain that the other has drifted. The settlement would also be a small and unusual population in its own right, founded by a limited group and carrying its own bottleneck, so neither party would be a fair sample of anything. There is a practical difficulty too, and it is one nobody has solved. The standards developed on Earth for keeping worlds biologically separate would be unenforceable at that distance, and probably unmeetable by either party. A ship that has carried its own simplified ecosystem for 400 years cannot be sterilized, and a settlement that has been living on a planet for 3 centuries is already thoroughly mixed with it. The question of who is allowed to land and on what terms would be decided entirely by the people present, using whatever principles they had left. Communication makes the isolation concrete in a way the distance figures do not. At the nearest star system, a message and its reply are separated by more than 8.5 years. That is not a delay. A delay is something you wait through. 8.5 years each way means that a question asked by one person is answered to a different person, and that no exchange of any kind can be completed within a working career. Earth is not a correspondent. Earth is an archive that occasionally adds to itself, and signals can simply stop. This is the possibility that has no comfortable reading. If Earth's transmissions ceased, the ship would have no way whatsoever to distinguish between a civilization that had ended, a civilization that had lost interest, a transmitter that had failed, and an antenna aboard the ship itself that had quietly gone out of alignment. All 4 produce identical silence. The crew would debate it for generations, and the debate would be unresolvable, and it would remain unresolvable forever. There is one architectural answer to all of this, and it is the same answer that keeps appearing whenever this subject is examined closely. Send more than one ship to more than one place. Redundancy in destination is the only insurance against being second, and multiplicity is the only insurance against being alone. A single ship to a single star is the most fragile version of the whole enterprise, and it is also, by a considerable margin, the cheapest, which is why it is the version most likely to be attempted first. And a second ship cannot help the first one, even if it wanted to. Matching velocity with a vessel already at cruise speed would require the newcomer to spend its entire braking budget on the rendezvous, leaving it unable to stop anywhere afterward. Coming alongside is not a favor that can be offered in passing. It is a whole mission spent to reach a ship that is doing fine. The faster vessel goes by at a relative speed of thousands of kilometers per second, and the 2 crews are within sight of one another for a fraction of a second, and then the distance opens again forever. It should be said plainly that neither of these outcomes was ever a reason not to go. The people who launch a generation ship are not launching it in the expectation of a clean result. They are launching it because the alternative is not launching it, and because a mission that produces a redundant arrival, or a lonely one, has still put human beings 4 light years from where they started. Every honest account of this enterprise has had to include the possibility that it accomplishes something other than what it intended. What it cannot include is the assumption that arriving and mattering are the same event. Those 2 things were joined together in everybody's imagination at departure, and the whole of this part is about the several ordinary ways in which they come apart. The ship can stop. The ship can be there. And the world can have moved on without it, either by getting there first or by ceasing to exist, and in neither case is there anything at all to be done except carry on maintaining the air. Part 11. The message that outlives the sender. A ship that never arrives is still talking. That is the quiet fact this part is built around, and it is one of the stranger consequences of the whole arrangement. The transmissions continue after the reason for them has gone, and they keep traveling long after everybody who composed them has died. The physics of interstellar communication is unforgiving, and it is worth going through gently because the difficulty is not where people usually expect. Radio signals do not weaken because something absorbs them. They weaken because they spread. A transmission leaves an antenna and expands outward as a shell, and the same amount of energy is smeared across a shell that grows larger every second, so the intensity falls with the square of the distance. Nothing stops the signal. It simply thins until no achievable receiver can separate it from the noise of the universe. The numbers from our own machines make the scale clear. The most distant working spacecraft we have managed something on the order of 160 bits per second from a few tens of astronomical units. That is a tiny trickle by any modern standard. A single photograph would take days, and it is simultaneously one of the great triumphs of engineering, because the power arriving at Earth from those transmitters is measured in fractions of a billionth of a watt. Stretch that to light years, and the requirement changes from a difficult problem to an enormous one. Very large apertures at both ends. Very narrow beams, which means very precise pointing, which must be maintained by a mechanism that has been running unattended for centuries, while both the sender and the receiver move. Very slow data rates, measured in bits rather than megabits. It can be done. It cannot be done casually, and it cannot be done by a system nobody is maintaining. There is one piece of mathematics that makes any of this possible, and it deserves a mention because it is genuinely elegant. Error-correcting codes allow a message to be reconstructed perfectly from a signal that has already been buried below the noise. Redundancy is built into the transmission in a structured way, so that a receiver which cannot hear individual bits reliably can still recover the whole. Without that technique, interstellar distance communication would not be worth discussing at all. With it, the question becomes one of patience rather than impossibility. Enough time and a slow enough data rate, and almost anything can be pulled out of the static. Light does better than radio, at least in principle. A laser can be focused into a far tighter beam than any radio antenna can manage, which concentrates the energy enormously and improves the arithmetic by orders of magnitude. The cost is pointing accuracy. A beam that narrow must be aimed with a precision that would have to be maintained by machinery running unattended for centuries, against a target that is moving, from a platform that is moving, with no opportunity to check whether it is working. It is the better technology and the more fragile one. A relay chain has been proposed as a way around all of this. Transmitters dropped along the route to pass messages forward in shorter hops. It is a sound idea that simply relocates the problem. Every relay is a machine left alone in interstellar space, expected to keep working for centuries, with nobody to maintain it and no way to know whether it has stopped. The asymmetry between the two ends is total, and it is the part worth sitting with. Earth learns of a failure years after it occurred. It has no capacity whatsoever to respond. It receives the report of a decision that was made, argued over, implemented and lived through by people who are already dead, and it receives it as news. Every message from the ship is a message from the past about a situation that has already resolved itself one way or the other. Picture the specific case. A ship discovers that its brake is gone. The crew confirms it, over months, with every test they can devise, and then composes a transmission and sends it home. That signal travels for years. It arrives at a receiving station on Earth and is decoded and read, and the people reading it understand that they are looking at an announcement of something that happened a long time ago, involving people who spent the rest of their lives with the knowledge and whose grandchildren are now running a ship that will not stop. And there is nothing to be done. The correct response is to write it down. The signal does not end at Earth either. Radio continues outward indefinitely, weakening but never actually stopping, which means the last report of a failed interstellar mission is technically still propagating and will be still propagating for the remaining life of the universe. It becomes undetectable long before it becomes non-existent. Somewhere out there, expanding at the speed of light through a volume that grows every second, is the sentence explaining what went wrong. The ship also carries an archive, and the archive is the part most likely to survive everything. We covered the material question earlier. Engraved metal and information written into fused quartz endure essentially without limit, while magnetic and optical storage fail within decades to centuries. What that produces at the end of all this is a rather remarkable object. A library, moving at a substantial fraction of the speed of light, structurally intact, chemically stable, radiation hardened by its own shielding, containing a complete account of a civilization, with no reader aboard, and none expected, and no plausible mechanism by which one might ever arrive. There is a further difficulty with the archive that has nothing to do with hardware, and it is the one least often anticipated. Even a perfectly preserved text in a perfectly preserved medium has to be read in a language, and language does not hold still. 4 centuries of drift is enough to make an unaided reading genuinely difficult, and that is before considering the technical vocabulary, the units, the conventions, the shorthand that every field develops and that becomes opaque within a generation or two of the people who invented it. A manual can be entirely intact, entirely legible, and entirely misleading, describing a procedure in terms whose meanings have quietly moved. That is a worse failure than illegibility, because an unreadable document announces its own uselessness, and a misunderstood one does not. The real probes we have already sent carry deliberate messages of exactly this kind. Engraved plates and a record disc, designed and assembled with great care on the explicit understanding that nobody would ever find them. They are best understood not as communications but as artifacts, statements made for the sake of making them, by people who wanted something of what they were to exist somewhere durable. A generation ship's archive would be the same gesture at an enormous scale. The standard proposal for escaping that trap is a layered archive. The deepest layer is written physically, at a size the human eye can read without any instrument whatsoever, and it explains in the simplest possible terms how to read the layer above it, which explains how to read the one above that. Each level bootstraps the next. It is a sensible design, and it has one obvious weakness, which is that the base layer must be written in a language somebody can still understand, and no method exists for guaranteeing that across the timescales involved. Detectability runs in the opposite direction from what one might guess, and this is the last turn of the part. A working starship is the loudest object imaginable in the infrared. It must dump enormous quantities of waste heat, and radiators large enough to do that cannot be hidden by any means physics allows. A living ship glows. It is the most detectable thing a civilization could put into space, and if anyone were looking for starships, the radiators are what they would find. A dead ship has no such signature. It cools to the temperature of its surroundings and becomes a cold body a few kilometers across, radiating at a handful of degrees above absolute zero, indistinguishable from nothing at all. So the visibility of the mission is highest while it is alive and falls to precisely zero when it ends. Which means the most likely condition of any derelict starship anywhere in this galaxy, if there are any, and across 100 billion stars and 10 billion years there may well be, is undetected and undetectable and traveling. The last thing to say about the message is the gentlest. Everything the ship ever sent home was composed by somebody who understood the arithmetic perfectly well. They knew the reply would come to their children or their grandchildren. They knew the news they were sending was already old. They sat down and composed it carefully anyway, in the way people have always written letters they were not certain would be read, and then they went back to work, and the signal went out into the dark ahead of them and behind them, and kept going. Part 12. The voyage was always the destination. The last part of tonight does not introduce a new way of failing. It reframes all the others, and it does so using the only evidence anybody actually has, which is the small fleet our species has already launched. There are 5 objects on trajectories that will carry them permanently out of the solar system. 2 were sent in the early 1970s. 2 more in 1977. 1 at the beginning of this century. That is the complete list. Everything else we have ever launched is still bound to the sun, and always will be. Not one of those 5 is going anywhere. Every one of them is a ship that will never arrive. The 2 earliest are already silent. One of them was last heard from at around 80 astronomical units, when its aging power supply fell below the level needed to push a signal across that distance. The other went quiet several years before that, for much the same reason. Neither is damaged in any way anybody knows of. Both are believed to be entirely intact, and both are still traveling at this moment, exactly as fast as they were on the day the last message came in, on exactly the same heading. Losing contact with a spacecraft is not the same as losing the spacecraft. The machine is fine. We simply cannot hear it anymore. The 2 launched in the late 1970s remain the most distant working instruments ever built. They are still returning data, and their power is declining year by year on a schedule everybody has known about since before they left. Instruments have been switched off, one at a time, deliberately, to keep the remaining ones alive a little longer. It is a slow and dignified retreat, managed carefully by people who mostly were not born when the mission launched, and it will end in the same silence the earlier pair reached. The most recent of the 5 crossed the outer solar system in this century and continues outward on the same kind of trajectory, with the same eventual outcome. It is worth noting how those 5 got out at all, because none of them did it by brute force. Achieving escape velocity from the sun by propulsion alone is beyond anything we have built. Every one of them was flung outward by the gravity of the outer planets, borrowing a small amount of orbital energy from worlds enormously more massive than themselves, and paying for the crossing with somebody else's momentum. 2 of them owe their trajectories to a rare alignment of the outer planets that made a single grand tour possible, an arrangement that recurs only about once every 175 years, and which happened to fall within the few decades when we had just become capable of using it. Their speeds are the reason they will never leave the galaxy. 17 kilometers per second is a magnificent figure for a machine built by hand on a planet, and it is a rounding error against the several hundred kilometers per second needed to escape the Milky Way. They will orbit the galactic center for as long as there is a galactic center to orbit, drifting slowly among stars that are themselves drifting, part of the disk rather than a departure from it. The slow retirement of the 2 working probes deserves a word of its own, because it is one of the quietly admirable things our species has done. Every instrument shut down was a deliberate trade, a capability given up in exchange for months or years of continued operation for the rest. Engineers have sat in rooms and chosen which senses to remove from a machine 4 times further from the sun than the outermost planet, in order to keep it alive a little longer, knowing the whole time that the end of the sequence is fixed and cannot be avoided. There is no version of this where the probes are saved. There is only the question of how gracefully they are allowed to finish. None of them has a destination. The headings that occasionally get quoted are true and misleading in equal measure. In roughly 40,000 years, one of them passes within about 1 7/10 of a light-year of a small nearby star. Another is aimed in the general direction of a bright red giant that it will reach in something like 2 million years. Both of those are statements about geometry, not about arrival. A separation of 1 7/10 of a light-year is more than a third of the distance from here to the nearest star. Nothing happens. Nothing is seen. The probe passes through a region where that star is merely the brightest point in an otherwise unremarkable sky, and carries on. And every one of them will remain structurally intact for hundreds of millions of years, and quite probably for billions, long after every building, monument, and carving on the surface of this planet has been ground away by weather and ice and the slow turning of the continents. The most durable things humanity has ever made are not in a museum, and they are not underground. They left decades ago, and they are not coming back, and they are not going anywhere either. That is the reframe this whole episode has been walking toward. A generation ship that never arrives has not failed into some unprecedented and terrible new condition. It has joined a category that already exists, that has 5 members, and that contains every single object our species has ever sent beyond the reach of the sun. Not arriving is not the exception. It is, so far, the only thing any of our interstellar machines has ever done. Which brings us back to where we started, and to the fact we set down in the first hour and left alone. A generation ship spends the overwhelming majority of its voyage with its engines off. Not because anything is wrong, and not because it is waiting for something, but because nothing is required. The vacuum asks nothing. The vessel moves because it was made to move, once, a very long time ago, and it will keep moving whether or not anybody aboard is watching, whether or not the mission still exists, whether or not there is anyone left to have a mission. We have been calling that the coast and treating it as a phase, the long middle stretch between the acceleration and the braking, the part in between the interesting parts. That was the wrong way round the entire time. The coast is not a phase of the voyage. The coast is what the voyage is. Arrival was only ever the scheduled interruption, a single planned event at one end of an enormous silence, requiring an intact brake and a correct target and a willing population and a great deal of luck arriving simultaneously after 400 years of not being needed. When that interruption does not come, nothing has gone wrong in any sense that the universe recognizes. No law has been broken. No system has misbehaved. The ship is simply continuing to do the one thing it has been doing since before anybody now living was born, which is to move, steadily, in a straight line, through a place with nothing in it. And that is a bleaker thought than it needs to be, so let us end somewhere else. Every one of these ships, in every one of these states, was full of people. People who woke at ordinary hours and did ordinary work and had ordinary arguments and raised children in corridors that were the only world any of them had known. People who tended a garden that had to work and repaired a machine that had to run and taught a child something they would need long after everybody in the room was gone. Whether the vessel stopped at the end or continued past it makes no difference at all to any of that. Those lives happened. They were not provisional. They were not a waiting room for an arrival that would make them count. A ship that never arrives is still a ship where somebody is asleep right now, in the quiet, with the air moving softly and the lights turned down, while outside the hull the stars hold almost perfectly still, because at these distances even a great speed is not enough to move them. And so the ship goes on the way it always has. Engines cold. Corridors warm. Everyone aboard asleep or awake at the usual hours, moving through a place so empty that nothing will ever slow it, on a heading set by people whose names are engraved on a plate somewhere inside. There is no moment when the voyage ends, because there was never a mechanism for ending it. There is only the long, steady drift, and the quiet, and the light of a star that was never quite reached, falling gently away behind. Let your breathing slow. Let the day fall away from you. Sleep well and good night.